Okay, so welcome to this lecture on analysis of algorithms, and we are going to be talking about this very interesting and important algorithm called binary search. And to be sure, binary search is a rather simple and elementary algorithm, at least as far as these algorithms go. But the most important thing about binary search is how to get it correct. And what we find typically is people struggle to get binary search correct, especially in one shot. So let's look at the binary search algorithm. So what is the binary search problem description? So it is a typical search problem. So you have a sorted list of numbers or a sorted list of keys. It could be a sorted list of strings, for example. And you are interested in whether a given key or a given element belongs to this sorted list. And being sorted is going to be really important because none of what I'm going to say will work if your list is not sorted. So let's talk about this. So here we have an example 1, 6, 7, 19, 22, 25, 31, and 55. And we are interested in knowing, does the element 18 exist in this list? And by the way, without loss of generality, I will assume that it's sorted in the ascending order. You can also work this when it's sorted in the descending order. Nothing really changes. It's just that the algorithm has to be rewritten with greater than replaced by less than. And you can do that as an exercise. Returning back to the example, if the element 18 is not part of the list, then the expected answer is false. On the other hand, here is another example of an ascending order sorted list. And we are interested in the element 6. And here, the answer is true because you do find the element 6, and you could return an index 1. Remember, indices in Python start from the index 0. So 0, 1, 2, 3, and so on, up to the length of the list minus 1. So in this case, you would return the answer 1 as the index, and you would also return true, and you could return a tuple with true and index. And in the previous case, you would return a tuple with false. And for the index, you would return a default or none. And that depends on how you choose to implement this problem. So then let us get into the basic idea of binary search. What is the basic idea? So let me illustrate this with a search for an element 6 in this list, which is sorted and goes from 1 to 25. Okay, and there are 7 elements in this list. And so what we start with is defining a search region by 2 pointers. And so these are going to be values of indices of the array, and we'll call them left and right. Okay, and the entire current search region is defined as the list between left and right with both ends inclusive. So currently this includes the entire list. And by the way, left would be 0, left would be 0. And right in this case would be how much? 0, 1, 2, 3, 4, 5, 6. There are 7 elements, so right is 6. The key step in binary search, and it's an iterative algorithm, at each iteration, you're going to search for the middle element, and you're going to check the middle element. And the middle element is simply given by left plus right. And you have to do an integer division. If it's an odd number, you have to round it down. And in Python, that's done by the double slash operator, divided by 2. And that gives you the middle element. In this case, this is the index 3. Okay. And at the index 3, you find the element 14, which is not what you're searching for. It's not what you're searching for. But what you're searching for, 6, is less than 14. So this clues you in that if I am to find 6, I better search in the left-hand side of this list. And so my new search region is going to have left equals 0, but my new right is simply going to be 1 to the left of my current middle element. So that would be 2. So now again, you do another iteration of binary search with this new updated search region. So another iteration with this new updated search region. And now mid becomes, in this iteration, 1. So you look at what is at index 1, and you find that it is in fact what you're searching for. So you're done, you exit early, and you return true. I did find what you're asking me to find. and you return the index at which you found it, which is index 1. I hope this is clear. So let's go into another example of binary search, just as an illustration. And here it's the same list, but we are now searching for the element 18. And how do we find that out? Well, let's start with, again, initially setting left to the very beginning of the list and setting right to the very end of the list. In this case, 6, in this case, 0. Again, mid is 3. And that looks at 14. In this example, you're searching for 18, which is greater than 14. And therefore, your search region now starts to become the right-hand side, the right half of the list where you're searching for, because your list is sorted in ascending order. The middle element is 14, and you're looking for something that's bigger than 14. So now you go and you say, okay, my new search region has left equals 4 and right remains 6. So at any time, you're just going to move one of these pointers and you're going to halve the search region, which is something I hope you notice. And then what you say is, okay, now let me do a new mid, which is mid is 6 plus 4 divided by 2. So that's 5. That's my new mid in this iteration. And if you look at this middle element, now 21 is greater than 18. So what you need to do is look to the left of 21, but also to the right of 17, because you already have narrowed the search region. So in the last iteration, you get left remains 4, but your new right in this iteration is also 4. Now, is this the end of binary search? No, you have to do one more iteration, because what you're saying here is, if I can find the element, I would find it in search region, which is between left and right, both ends inclusive. And so when you say, okay, if I can find it, I'll find it at 4. So let's do one more iteration. Okay, in this iteration, what happens is mid, which is left plus right. So mid, which is left plus right by 2, is also 4, which kind of trivializes it. And you say at this 4, you find the element 17 is less than what you're searching for, which is 18. So now something strange is done. What you do is you follow the same rule and you say, okay, then I have to find things to the right of 4. So therefore, what happens is left now ends up being one more, which is 5, and right ends up being 4. So what happens here is your left and right pointers end up crossing over. And when they end up crossing over, you will have to declare that there is no way that I can find 18. So there is no way to find the element 18 in this list. And so you would basically bail out at this point and say that you failed to return this element. In fact, there's a little bit of extra information if you care to extract it, which is you also know that if the element were to be found in the list, where would it be found in the list? Okay, so that's a little bit of an extra thing, which we won't care about at this point. All right, so with hopefully the idea of binary search clear, let's look at how would we implement binary search. And the easiest implementation would be to do a recursive implementation. Though I have uploaded some notes where I show you that it's also possible very easily to do a loop-based implementation. So let me define a function here called binary search helper, which is going to help me in binary search. And I'm going to call this function from my main function. So I'm going to create a main binary search function in the very next slide, and that function will call helper. So right now, helper is going to help me in the middle of my binary search. And you have an ascending sorted list here. Okay, I'm just representing it like this: smallest element here, largest element here. And somewhere in this list, you have defined a search region right now between some index left, some index here, let's call it left, and some index here, let's call it right. Okay, so you know that if the element were to be found, it's going to be found between left and right. Okay, and that's the property that you're going to keep maintaining. And this kind of a property is called an invariant. So you have to maintain two things. One is when you're going to call binary search helper, make sure that left and right are such that left is less than or equal to right, and also make sure that you have 0 is going to be less than or equal to the left, which is going to be less than the size of the list. Okay, so these are going to be important properties that you need to maintain. Okay, so the very first thing I will do is to make sure that if indeed this requirement that I just stated fails, which is if left and right have crossed over, then let me just declare that there is no way to find this element. So let me return false and not bother returning an index. In Python, you could do that by calling that none. So that's very important. So first, let's do that. Then second, let's also have the following, which is let us say that otherwise else, what we do is we compute mid, which is going to be left plus right divided by 2. Okay, and now you have to do a comparison. So I'm going to write the rest of the code here. All right, so I'm going to say if the list at mid equals what I'm searching for, which is I'm searching for the element, then of course I'm going to return true. I'm going to return true right away. I found what you're looking for, and I'm going to return the index, which is at mid. So that's the good part. Else, what I'm going to do, there are two cases left. So first case is if list of mid is less than the element, then I have to do something. Else, if list of mid is greater than the element, I have to do something else. Now, what are these something else? Let me just go to the next slide where I have the code written and just show you the code. Okay, so here is the full code here. And you can see that if left is greater than right, I return none. I say mid is left plus right divided by 2. If I find the mid element, then just return the mid element. Otherwise, what do? I'm going to call binary search again on the same list, looking for the same element, but my new search region is mid plus 1, right. Why is that? Because here's the list, here's the search region, and I've looked at mid, okay, and this element here, list of mid, is less than what I'm looking for. So what I'm looking for better be here if it's at all to be found. So my search region becomes mid plus 1 to right. On the other hand, if the mid element is greater than what I'm looking for, then the search region becomes between left and mid minus 1. Okay, and that's the algorithm. It's just 4 lines, but you have to be careful when you're writing the 4 lines. And instead of returning true and false, I simply return none. I simply return none when I cannot find it, or I return a number. I return a number when I can find it. And that can be made into true and false if you know how. Okay, so this is just a small variation on what I have been talking about so far, but hopefully you know enough Python that it doesn't trip you up. All right. And here is how you would call binary search. You would simply say, let me call binary search helper on the list, on the element that you're being asked to find, and let me initialize left to 0, and let me initialize right to size of list minus 1. Okay, so this is going to be important. So you have to initialize left and right correctly, and you're all set. Okay, once you have initialized it correctly, the helper function takes care of the rest. I hope this is okay. All right. Now, one of the nice things about binary search is you can now start to argue why is binary search correct. Okay, and what you have to show is the following behavior for binary search helper. So you have to show that if the list is sorted in ascending order, and if the element belongs to this sublist, list of left to list of right, which defines the search region, then binary search will correctly return the index of the element that you're searching for. If the list does not belong to the sublist, then binary search will return special value none, which is just a variant. Previously, I said false. you can just turn it into a special value none. And previously I said here true. And instead you can say, let me just return a number, which is the index of the list where you can find the element. And the true becomes redundant. The false becomes redundant. It's just a small implementation change. All right. So how does that work? Well, what you show is the following property, that if you call binary search helper, it's going to maintain this invariant property that anytime you call binary search helper, and let's say there is a list and there is an element you're searching for in that list, and you have a search region that I'm showing in blue, left and right, then binary search helper always has this property that if I can find element in the entire list, it would be found in the search region. This is important. So this is the main property I'm going to maintain. And the way I maintain it is by showing that if in a particular iteration of binary search, this property holds, then given that it's a recursive function, this binary search is going to call new instance of binary search helper. So binary search helper is going to call another instance of binary search helper. So it's going to call another instance of binary search helper. And that's what recursion does. Okay. Let me just say binary search helper. So what you have to show is that if this property holds here, then it's maintained in the next call, And that's very important. And that's called an induction argument. In the notes that I have provided to accompany this lecture, you can see how the induction argument goes. And I have given it in a lot of detail. You typically don't need that level of detail, but I just wanted to demonstrate a couple of algorithms at that level of detail, just so that you know. Another interesting activity is to look at how long will binary search take on an array of size n. So what happens when you call binary search on an array of size n? And to make life easy, we can always say n is some power of k. Let's call it 2 to the power k. Just as an example, 2 to the power 10 is 1024. So let's say n is 1024. So what happens with binary search? Suppose you're searching for an element in this array. So in binary search, at every iteration of the algorithm, your search region gets halved or less than halved. So you're going to, if you start with the search region initially, that's your entire list, then in one iteration, you're going to say it's either the left side of the list or the right side of the list. And then in the next iteration, you further halved your search region. In the next iteration, you further halved your search region. In the next iteration, you further halved your search region until your search region becomes of size 1, and then you stop in a further iteration. So in the worst case, and you could have stopped earlier, you could have stopped in the very first iteration if by luck, your middle element was already what you're searching for, right? If you've already, what you're searching for is in the middle element of the list and you already found it, then you're done. And that's the lucky condition, right? And that will not happen in the worst case. In the worst case, you're forced to go all the way down, grind all the way down until your left and right pointers cross over and you declare that the element is not in the list, or otherwise you find it at the very last step. But if you go one step, and if your original array is of size n, then your new array is of size less than or equal to n by 2, in this case 2 to the power k minus 1. And then if you go one more step, and this is in step 1, in step 2, your new array would be n by 4, which is 2 to the power k minus 2. So at every step, you're halving the size of the array. And the question is, in how many steps will I reach an array of size 1? And you can conclude, in this case, that you go from 2 to the k minus 1, 2 to the k minus 2 in 2 steps, 2 to the k minus 3 in 3 steps, 2 to the k minus k, which is 1 in k steps. So you can claim that at most, k plus 1 steps, where k is in fact log to the base 2 of n. If n is 2 to the k, then k is log to the base 2 of n. So this analysis, and you can put a big theta notation around it, and that requires a little bit of an extra step in proving a lower bound, which I won't go here. At least we can put a big O notation from everything I have said here. You can at least put a big O notation, and that will convince you that at least we have shown that binary search has complexity O log n. It's upper bounded by log n. A little bit more work, and you can look up the book on how you prove lower bounds. You can also show that it's big theta log n for this algorithm. All right. So that's about the running time analysis of binary search. And this is very good news for us, because let us say you want to search an array of 1 million, which is 10 to the 9, approximately 2 to the power 20 elements in your array. So you can show that in roughly 21 binary search steps, you can either zero in on an element, or you can conclude it doesn't exist. And this is the worst case. So suppose you have, let's say 1 trillion, 1,000, this was for 1 billion. Let's say you have 1 trillion, which is 10 to the 12, which is about 2 to the power, let's say 30. Well, then it's just 30 steps, or at most 31 steps here, which is really, really good. A trillion is a big number, and you can search this rather fast. So binary search is one of these very nice algorithms that's considered really, really fast. And of course, it only works when the array is sorted. So I hope this was informative, and I have a lot more details, in fact, too much details in the Jupyter notebook that I have attached with this lecture. So I hope you are able to take a look at that and understand a little bit more details on how correctness can be established. Thank you.